Here's a problem similar to what you're going to be asked to do in the lab, where we have two stars and each one has a mass of 300, so they are identical. And I've put each of them 300 units away from the origin here. And I'm going to hit start, and they're going to start falling together. And I want to figure out how fast will they be moving when they are here and here. And so we have some definitions here. There's an initial separation between them. I'm going to call R initial. And if you look down here, if each one's 300, we know that's 600. And then there's an R final. And so if each grid is 100 units, R final is 200. And so we want to use conservation of energy to predict what these speeds will be. Since they're the same mass, they'll both have the same speed, opposite direction, so opposite sign velocity. And to do something like this, we want to use conservation of energy, and so the initial energy equals the final energy. The initial energy is all potential, so UG initial, and the final energy, we have potential, and we also have kinetic. The initial energy is potential, but remember, gravitational potential energy is negative Gmm over R. Very similar to the force of gravity equation, so you got to watch that. There's a minus sign that is part of the equation, and it's just over R, not over R squared. And so over here, that would be negative Gm, and they're both the same mass, so I'll put two big M's, and then over R initial. And then the final energy is negative Gmm over R final. And so also notice I just put one term. You need two objects to have potential energy. And so we have these two masses. Together they have potential energy. If there's only one mass, there's no potential energy, gravitational potential energy. But kinetic energy, each one has its own kinetic energy. So I have a term for one star. So I'm going to call that V final. That's what we're solving for, V final here. And I have a term for the other star. And I'm going to write each term separately just in case they're different masses, then I'd have to do that. But these are both the same mass, so they are going to have the same speed. So it looks kind of complicated, but we can get some simplification. There's an M in every term, so we can divide that out. And so I get, I get no room here. We can do this. And so I get negative Gm over R initial is negative Gm over R final. And then here I have a Vf squared over 2 and another Vf squared over 2. So that's just Vf squared. And so I can solve for V final. It's going to be the square roots. And I'm going to skip a few steps in algebra here, but you can see I need to add this term over here, and then I can factor that Gm out. And so I get 1 over R final minus 1 over R initial. And we are using the simulations values for G and using the units of the simulation. And so V final is 10,000 times 300, the mass, over 1 over R final, which was 200, minus 1 over R initial. If you use the x to the minus 1 button on your calculator, it makes this part a little easier. And it comes out to 100, whatever the units are, distance over time. So let's check that out. And so I'm going to hit start. So they're falling together, and I'm going to hit stop right, hopefully when they're close to 200 apart. See how quick I can do that. Oh, a little off. And so they're going 103, so they went a little faster, but that is close enough. Now you have to watch whether you want to, you don't want to memorize this as an equation. You want to be able to derive it. For example, I could give you this problem where they both have an initial velocity either this way or that way. And so you have to be able to handle that. And you would handle that by adding kinetic energy over here too. And so I can change this up. Don't just memorize a final answer. Start with conservation of energy and work through it. Do that on the lab too. Good luck.